As promised, this is your physics thermodynamics review. We're going to start by just reviewing units. Heat has a symbol of Q. Work's symbol is W. Energy, any kind of energy, symbol is E. So that could be E as in potential energy, kinetic energy. The one that we've talked about in thermodynamics is the internal energy. Those all have units of joules because they're all related to energy. It's either just the energy, or it's heat, which is a transfer of thermal energy, or it's work, which is a way to change the energy of a system by exerting a force through a distance. Those all have units of joules because they really are essentially the same thing. Next we have temperature. The symbol is capital T, and that can be Celsius or Kelvin, but I'm highlighting Kelvin because Kelvin is the unit that it needs to be in the gas laws, any of the gas laws relationships, in the efficiency equation. When in doubt, Kelvin is good. Anytime the temperature could be in the denominator, you could be dividing by temperature, then it's required that that is Kelvin because you can't divide by 0. You convert from Celsius to Kelvin by adding 273. That's on your equation sheet. Pressure, the symbol is capital P, and the units that we use different ones in chemistry, but the units we'll use in physics here are pascals, which is a Newton per meter squared. So pressure is a force exerted on a certain area, Newton per square meter, and we've used pascals for that so that we stay in our KMS units. Volume, the symbol is capital V, and again, KMS units, we're going to do meters cubed. Moles, the symbol is N, and that's just moles. The gas constant R, we're using from PV equals nRT, pascals for the pressure, meters cubed from the volume, moles for the moles, and Kelvin for the temperature. So technically it's Pascal meter cubed per mole Kelvin, but a Pascal is just a Newton per square meter times meters cubed. Meters cubed over meters squared is just meters, so Newton times meter, that's a joule. So really, when we use those units of pascals for pressure, cubic meter for volume, moles for moles, Kelvin for temperature, we end up with, really, that's just joule per mole Kelvin. And the value that we use is 8.3 joule per mole Kelvin. Hopefully you have figured that out. And those joules are okay because a joule does come from our KMS units, kilograms, meters, and seconds. As long as everything is in some form of kilogram, meter, and second, the units will all work out. If you use the units listed above, everything will be fine. Please make sure you have worked through enough of those problems that you won't run into any trouble on the test. Okay, this is the summary sheet that I passed out in class, and this is just a summary of some things that you can do, things that can happen when you add heat to a substance. First of all, it could change temperature. If you have a single state of matter, a solid, a liquid, or a gas, and you add heat to it, well, its temperature will change. The average kinetic energy of the particles will increase, its temperature will change. So the equation that would apply for a single state of matter that you add Q to is Q equals mc delta T. So if you add or remove heat, the temperature will change. The amount of mass is a factor in that, and also that's M, and also C, that is the specific heat capacity of the material. That is going to be different for every material. Aluminum is different than iron, is different than water. Those values will be given to you. You don't need to write any of them down. Number 2, it could change phase. So if it is at a melting point or a boiling point, then you would have a phase change. And the equation is Q equals mL on your equation sheet, I believe, for that. So I added that in there. So if you add Q to a material at its melting point or at its boiling point, then the material will increase its internal energy because of a phase change. There is no temperature change during a phase change, during the process of melting or the process of freezing, the process of boiling, or the process of condensing. There is no temperature change. Those are all related to your heat and temperature graph, which we'll talk about on the next slide. Number 3, it could change its size. So this is thermal expansion that you did calculations for. It could change length, area, or volume, whichever one you would choose, would just be depending what the problem is asking you for. And the factors there are alpha, that is a coefficient of thermal expansion, It's going to tell you how much that material expands. And again, unique to the material, different for aluminum versus iron versus copper. The original length, area, or volume, and then the change in temperature. So, as would make sense, if you increase its temperature more, you're going to undergo a more change in size. How can you add heat to your stuff? Well, we've got convection, radiation, and conduction. Conduction is two solids in contact. Capital H is the rate of heat transfer, so Q over lowercase t. And so that's describing how fast the energy transfers. If you are transferring energy through a styrofoam cooler, that is going to be different than the rate of heat transfer through a piece of aluminum. So the equation that tells you about the rate of heat transfer, K, capital A, delta T over capital L. K, on this little picture here on the bottom right, is showing you that that's unique to the material. Coefficient of thermal conductivity. So again, it's different for every material. We have quite a few of these and those kind of quantities in this unit. Capital A is the area in contact. Delta T is referring to the temperature difference from the two sides. And then L would be the thickness. So a thicker piece of styrofoam, you have a bigger number in the denominator, it would reduce the rate of heat transfer. If you have more area in contact, if you have bigger windows in your house instead of smaller windows, you will increase the area. Increasing the area will increase the rate of heat transfer. If you have a material that is really good at transferring heat with a big value of K, like a metal, that would increase the rate of heat transfer. And then the bigger temperature change, that's going to be a bigger driving force to cause that rate of heat transfer. So this heat will transfer until you reach thermal equilibrium, which would be when delta T, the difference in temperature, is 0. When you have a common temperature reached, then your heat transfer would stop. So this is our graph for Q versus T, one way of showing that graph. So we've got kilojoules, we've got temperature and degrees Celsius. So just to make sure we know what all the parts are here, we have 3 states of matter, solid, liquid, and gas. The one at the lowest temperature value is the solid, middle is the liquid, the highest is the gas. The vertical portions, those vertical portions are showing where there is no temperature change. As you go from, one end of the line segment to the other for those vertical portions, there is no temperature change. So that tells you that that's a phase change. So to summarize, when you have a slope in the solid, the liquid, and the gas portions, that's when you use Q equals MC delta T. When you have no temperature change, that's when you use Q equals ML. You can have more than one of those processes happening. You could have, first you have to heat the liquid to the boiling point. That would be a Q equals MC delta T calculation. And then it all boils and turns into a gas. That would be a Q equals ML. Calculate the value for each line segment and add them up. Again, make sure you've practiced those problems in homework that relate to Q equals MC delta T and Q equals ML. Summarizing our big equation sheet on the back, you have PV equals nRT, ideal gas law. That could be a question just in and of itself, doing a calculation with ideal gas law. We have delta E internal equals work in plus Q in. That is the first law of thermodynamics in equation form. First law of thermodynamics says that energy is not created or destroyed. We have P1 V1 over N1 T1 equals P2 V2 over N2 T2. That's your most general form of like the before and after equations of the gas laws. If, say, moles were constant, then you just cross them out from both sides. That's the most general form, though. And then we have that work for a constant pressure situation is negative P delta V. So if pressure is constant, you can calculate the work using the negative P delta V equation. If it's not constant, then you need to use your pressure volume graph. The area under the curve of a pressure volume graph is the work. The area is just going to be a calculation, either a triangle or a triangle plus a rectangle or just a rectangle. Something that you could do, and then you have to decide whether it's positive or negative. The area calculation won't tell you positive or negative. You decide whether it's positive or negative based on did the piston move in or the piston move out? If the piston moved in, that would correspond to a decrease in volume. Push the piston in, decrease in volume. So piston in, work in, positive work. That is positive work done on the gas. If the piston moves out, that's work out. That is negative work. The gas essentially did work on the surroundings. If it's an engine, that's the part that you want, is for your piston to do work on, or your gas to do work on the surroundings. Okay, we have isobaric. We started here with isochoric. Isochoric is constant volume. There is no work done in a constant volume situation. Zero work because the volume didn't change. So any change in internal energy is just going to be related to the heat. So if you put heat in, change in internal energy is equal to the heat. If you have positive Q, that means that you're going to have a positive change in internal energy. Internal energy tracks with temperature. If you have a trapped gas and you put a flame underneath it, you are adding Q. That is going to increase the internal energy. Increasing internal energy means increase in temperature. Based on the equation P1 over T1 equals P2 over T2, increase in temperature means an increase in pressure. That should make sense to you. That's the don't ever do this aerosol can in a campfire, right? You have a constant volume situation, adding Q, pressure will increase, and that's why that could potentially explode, and you should never ever do that. Okay, isobaric is constant pressure. The pressure is not changing. In an isobaric situation, you do have work done. In this particular case, if you go from A to B, that's piston out, increase in volume, piston out, work out, negative work. So in this case, from A to B, you can also figure out what happens with temperature. Because for temperature, you can get temperature from a pressure-volume graph based on the multiplication of pressure and volume. The product of pressure and volume. In this case, at point A, you have a big pressure and multiplied by a small volume. And then at point B, you have a big pressure multiplied by a big volume. So point B is at a higher temperature. Point B is at a higher temperature. The gas at point B is at a higher temperature. So higher temperature means that you have positive delta E internal. And you know that you have negative work. You had a quiz to this effect. That we know we have positive delta E internal. We know we did negative work based on what happened to the piston. In this case, our Q would have to be a big positive number so that the left side could equal the right side. Okay, if you have a positive change in internal energy, but negative work, you'd have to have add a lot of heat to cause this to happen, so that those can, so that the left side can still equal the right side. Okay. So, and make sure that matches up with our gas law. If we increase the volume, volume and temperature are directly proportional in this equation. So if we increase the volume, it increases the temperature. Yes, that matches with an increase in our internal energy. Should all be telling, all four boxes should be telling the same story. Isothermal, those lines, those curvy lines there are called isotherms. Those are lines of constant temperature. Isothermal, we reduced to Boyle's law here because temperature does not change. That's what isothermal means. It does not mean that Q is zero because heat and temperature are not the same thing. Constant temperature, not zero Q. So what is zero, though, is our change in internal energy because change in internal energy tracks with temperature. If your temperature did not change, you did not change internal energy. If we go from A to B, then we have increase the volume, piston out, work out. That would be negative. Q would have to be positive so that the left side could equal zero. Pressure and volume have an inverse relationship. When we increase the volume, in order to keep that at constant temperature, we have to decrease the pressure. It's the only way it can work out. Adiabatic means that now Q is zero. So that means that our first law equation reduces to change in internal energy is going to correspond to the work. In this particular example, if we go from A to B, that is piston out, work out, negative work. So if Q is zero, because it's adiabatic, means no heat is added, that means well insulated, that's how you would accomplish that, then you would have to have a decrease in the internal energy. That's the only way that the left side of the equation could equal the right side of the equation. Notice that that line for adiabatic, the adiabat, is not the same as an isotherm. Look at the difference there, how you can tell the difference between an isotherm and an adiabat. Okay, let's see here. So, all right, and so the engine cycle says that we are ending up where we start. To have an engine cycle, you have to end up back at A so that you can repeat the process over again. It doesn't have to look exactly like this, but it has to be a closed structure. It would not be okay to have a PV graph that looked like, let me make it something different, that looked like that. That is not an engine cycle because you didn't end up back where you started. You have to end up back where you started. The piston and the initial conditions have to end up at where they started so that it can be repetitive. You don't want to just run an engine one time through. Okay, you have two equations there for efficiency. Q hot minus Q cold over Q hot. Q hot minus Q cold is just the work done. And then you have the Carnot efficiency. That's what EC is. That's T hot minus T cold over T hot. That's a theoretical, an ideal efficiency, assuming everything is as perfect as you could get it. Let's do an example back here. So here's our equations for efficiency. If you know the work and you know the joules that left from the hot reservoir. The hot reservoir is basically the boiler. It's the that's what you get when you do the nuclear reaction in the nuclear power plant, or you burn the coal in the locomotive. The ideal efficiency is just based on temperatures. These temperatures have to be in Kelvin for the Carnot efficiency. Must be in Kelvin. Okay, let's look at our example here. We have an engine that goes that has a hot reservoir at 600 Kelvin, a cold reservoir at 300 Kelvin. We have 10 joules of energy leaving the hot reservoir, 6 joules going to the cold reservoir, 4 joules leaves as useful work. So to calculate our efficiencies, we have Q hot minus Q cold, 10 joules minus 6 joules over 10 joules. 4 joules over 10 joules. Notice that the joules cancel and you end up with 0.4. Convert that to a percentage, that's 40%.